Physics Notes, Unit 21, Circuits, Combinations of Resistors, and Kirchhoff's Laws. First, a review of some of the old equations that will still be in play here. The first one here, definition of current, I equals delta Q, the charge flow per unit of time. Second one, Ohm's law. It's technically delta V, but we now are going to drop the delta in all these problems just to make it a little bit simpler. Electrical power equals potential difference times the current. Other combinations can also give us power as I squared R, and there's other versions as well. Power is V squared over R. That's the third one. And then an old equation from mechanical power that also connects with electrical power. Power is energy over time, and if you rework that, you get energy equals power times time. So we'll be using all those again. Some new things over here on the right, at least slightly new. This represents connections of resistors. Usually when we have resistors, we don't draw them as little rectangles like this. The letter R here stands for resistor, but usually they're going to be little squiggle, little zigzags. So it's going to be like a zigzag instead of so it'll be a sawtooth. Those are two resistors. And down here, these are in parallel, which I'm going to talk about. And you can have 3 or 4 or 5 in parallel. We did capacitors in parallel in series already as well. And the rules are similar, but there's subtle differences. They're kind of reversed. For capacitors in series, you have to do the 1 over mathematics for the capacitors in series, and then the arithmetic sum for them in parallel. So the rules kind of flipped here, and we do a lot more of these than we do for capacitor problems. Let me explain. In the top here, we have a series connection. Scroll down a little bit. Definition of series, once again, we talked about this with capacitors for a little bit. There's a single pathway. We say it's a single branch. Like if you were going to label these, I'm going to go back up to the top here. If I call that point A and this point B, if I were traveling along that path, it's a single road, and I have to go through both resistors. They're in series. You could have 3 or 4 or 5 in that roadway. We call that a branch. So they're in series. As opposed to the second situation down here, if I call this point A and this point B, now if I went from point A to point B, I have 2 different roads, 2 different pathways. Each of those pathways is called a branch. Each of those dots is called a junction. We'll define that more specifically in a little bit here. It's called a junction. And there's another junction up here, that dot. It's a fork in the road. It's a split in the path. So both those arrows are supposed to be pointing towards those dots. So a parallel connection is multiple branches. Could be as few as 2 like we have in that diagram, or it could be 3 or 4 or 5. But the math is very similar to when we had capacitors in series. So we'll practice this. One thing I skipped over a little bit here, which will be exemplified in the examples. Resistors in parallel, like that second situation there, all have the same delta V, same potential difference, same voltage. And at the top of the page here, in series, they all have the same current flow, same number of coulombs per second, same number of electrons that have to go through each one. In a parallel situation down here, if 100 electrons start at point A and you want to get to point B, more of them are going to go through the easier path, the path with less resistance. So say if resistor 1 has less resistance, more of those 100 electrons will go through that pathway. If both resistors have the same resistance, it'll split up 50%, 50%. So if 100 electrons are at point A, 50 will go through resistor 1 and 50 will go through resistor 2. All right, let's practice some of this. So I've already done part A here, but it's pretty straightforward. There's almost no issues with this type of problem. If you connect resistors in series, and they don't have to be in order from lowest to highest, you can put them in any order here. But this is just a single branch, a single pathway from point A to point B, and you just add those 4 resistances together and you get 135 ohms. So those 4 resistors in series are acting as if the simplified diagram here on the right is true. They can be replaced by a 135 ohm resistor. All right, let me draw out the parallel situation. So I've drawn this out. You might need to pause this. Here's 4 resistors in parallel. There could be 3, 4, 5. Here's 3. And all the connecting red lines are wires. It doesn't matter how long the wires are. It's not a matter of how short a path is. Like the 55 ohm resistors way down here at the bottom, it's going to be a high resistance path. So the only reason why there's not going to be a whole lot of current down there eventually is because there's a lot of resistance, not because it's far away. So it has nothing to do with how far away you are from point A or point B as far as the current and the resistance is concerned. So there's 4 pathways to get from A to B. There's 4 resistors in parallel. So here's the math, and I've gone through every step, and whatever it takes for you to do this right or to get the right answer, what I prefer is that if you're doing homework, you show the initial setup, this one right here, 1 over R total equals 1 over 15 plus 1 over 25. As long as they're all the same units, you can skip the units till the end. But I don't need to see all these intermediate steps. You can if you want, but here's one way to do it without having to find common denominators, because you don't want to mess with common denominators. Turn this all into decimals, like 1 over 15 is 0.067, 1 over 25 is 0.040, 1 over 40 is 0.025, and 1 over 55 is 0.018. Add those 4 decimal numbers together and you get 0.15. 0.150. So if 1 over R total equals 0.15, now one of the common mistakes is some people will think that's the final answer, 0.15. No, that's 1 over. That's the inverse of the resistance. So if 1 over the total resistance is 0.15, that means the total resistance is 1 over 0.15. You switch those two around, or you take the reciprocal of both. So the total combined resistance here is 6.7 ohms. So you could redraw this diagram, the equivalent diagram. If you want to draw, it might ask you to draw the equivalent diagram. Well, the equivalent diagram would just be drawing a 6.7 ohm resistor. Could replace all 4 of those resistors. So what you find is when you have resistors in parallel, the overall resistance is less. The more resistors you add, the less resistance you get, because you have more pathways. It's like building more roads from point A to point B, even if it's a bad road. Like here, the 55 ohm resistor would be like a bad road, a road that people wouldn't want to take because it's a lot of resistance. But it's still true. The more resistors you add, even if you add a high resistance resistor, the overall resistance will go down. And the overall resistance is always less than the smallest of the resistors. So the smallest resistor here is 15. So when you're in parallel, your answer will always be smaller than the smallest answer. So keep that in mind of the smallest resistors that you start with. In series, every time you add a resistor, the overall resistance goes up. And if that's a circuit, you'd end up with less current in that circuit. Because the more, it's like putting more potholes in a road. The more potholes and resistance you have, the more difficult it is to get down the road, the fewer cars, the less current you're going to have in that circuit. All right, part C is one more part here. Let me draw it over here to the right. Let me see if I can squeeze it in. Okay, so here's the diagram for C. You have the 15 ohm resistor in series with the other 3 in parallel. So we start with the 3 that are in parallel, the 25, the 40, and the 50. So you see that here combining in parallel, 1 over 25 plus 1 over 40 plus 1 over 55. Put those in decimal form, add the decimals together, you get 1 over R total for that part of the circuit is 0.083. So R total for those 3, I always use a T for the total there. That 12 ohms is representative of the 3 that are put together. That's their combined resistance. But I want the overall resistance in the circuit, so I'm calling it R sub T2. Because the 15 ohm resistor up here is in series with all of that. So now it's in series. It's going to be 15 plus 12 is 27. So the total resistance is 27 ohms. All right. All right, now we have a much more complex circuit. We have a battery right here. And we have 5 resistors. Some are in series, some are in parallel. It's a network of resistors. And the question is, where do you start? And we've had a little practice with capacitors. It's fairly obvious, I hope, that the 13.8 and the 17.2 ohm resistors are in parallel with each other. Not only are they parallel lines, but they are 2 pathways from point B to point C. All right, they are on that branch. There's a branch from B to C, but each one is an individual branch. There's a junction. I'll put a red dot here. There's a junction basically right here and right here, or is it split in the path? There's also a junction at these other spots out here, which are basically lead-ins to that parallel part right here of the 13 and the 7. So we're going to combine those as parallel. Now another tricky thing is, if I'm at point B, I can go around this way to get to point C. Now on some visual aspect, the 4.11 and the 8.45 look like they're in parallel with each other. They're on parallel lines, but they're in one branch. They are in series with each other. That's a little tricky because they're on one pathway, one road, even though the road turns and curves a little, turns. From B to over here, down here, over to C, that's one pathway. They are in series. So I'm going to do two moves here at once and then draw a new diagram, and that's one of the keys in these complex circuits, is I'm going to do two things in one step and then redraw the diagram. But basically I'm going to do 1 over R total equals 1 over 13.8 plus 1 over 17.2. And once again, if I do all the math there, I get 1 over R total equals 0.072 plus 0.058. Okay, I get 1 over R total equals 0.13, I believe. 0.13, and then I flip that over. R total is going to be 1 over that, 7.7 ohms. I'm going to circle that. That's important. It's not my final answer. But then I also have 4.11 plus 8.45, which is 12. Okay, so I'm doing another computation here. So these are all generic. That T is just a generic. It's just going to be 8.45 plus 4.11. So our total there is 12.56. So it's 4 sig figs. I'm going to round off eventually here. But I'm going to draw this diagram with a simplified version. And here it is. You might need to pause and draw this down. But the 40-volt battery down here at the bottom, the 15 ohm resistor didn't change, but I've replaced the 13.8 and the 17.2 with that equivalent 7.7. Now that's one branch. And then we have the 12.56, which replaced the 8.45 and the 4.11. And you can put that anywhere on this branch over here, and that is its equivalent. And still up here, this is point B up here still. That's point B. And this is point C. All right, now here it gets a little bit tricky maybe. If these are roads, that's how I treat them, and the long side of the battery is the positive side. If I were to take a walk, a hike, there's millions of electrons everywhere, but if I was one of the electrons, or protons, but I'm going to take a walk. I'm going to walk over this way, up this way, I'm going on a hike. Once I get to point B, now I have a choice. That means I'm at my first split in the road. That's a junction. Now I'm going to head into a parallel situation. I can go around here to the 12.56 and get to C. Or once I'm at point B, I can go straight down. That means the 7.7 and the 12.56 are in parallel with each other. They are not in parallel with the 15. It looks like they are, but they're not. Right? Because once again, if I start at, well, even if I start at point C and go this way, hike, and I hike through the battery, hit this corner, go up this way, and go this way, the only time I have to split is when I'm at B. We'd say the 15 ohm resistor is in series with the battery. We'll come back to that. But the 7.7 and the 12.56 are in parallel. So I'm going to come over here to the left, and I'm going to combine them. I'm going to take, once again, I'm going to do the same math. 1 over R total. Once again, I'm using T as a generic letter here. Equals 1 over 7.7 plus 1 over 12.56. You could have rounded that off to 12.6 or 13. So 1 over R total equals 0.13. Oops, that's 0.13. Well, we already knew that, basically. 0.13 plus 0.08. So you have 1 over R total equals 0.21. So R total combined for the 7.7 and the 12.56 is 4.8 ohms. 4.8 ohms. All right. Get down here a little bit. Okay. Well, I'm going to draw a new diagram again. I'm going to draw a diagram that replaces those two with a single resistor. You can see how we're trying to simplify things. So here it is. I've replaced the 7.7 and the 12.56 with the 4.8 ohm resistor. And now B and C, points B and C are immaterial. We have one loop here now. It's one path. So the 15 and the 4.8 are in series with each other. And I'm going to round off a little bit to make this problem go a little faster. But if they're in series, there's a single path. It's a single road, even though there's turns. The final circuit, the final simplified circuit, is just, hang on. Here's the final diagram. 40 volts. Technically, 15 plus 4.8 is 19.8. So I took 19.8 and rounded it off to 20 ohms to help us move along here a little bit. Okay, now once you get to this final diagram, these diagrams are important. Now we're going to apply Ohm's law. We're going to apply Ohm's law. I'm going to use V equals IR. So I do V equals IR. Well, this one's pretty simple. The V is 40. I unknown. R is 20. That's the total. We call that the total circuit resistance. So the current in this little diagram down here will be 2.0 amps. 2 amps. All right? Now, so one thing you'll be seeing on future problems is that we start to draw arrows on our diagram. And the colors are kind of helpful. But what that means here is that there's a current flow here in this loop. That blue arrow represents the flow of charge in the wires, 2.0 amps. So there's 2.0 amps, so I'm going to write that down, 2.0 amps of current, coulombs per second, going through the resistor and going through the battery everywhere. Every point in that loop, like you saw in the simulation, everything's moving like musical chairs at 2 coulombs per second, passing each point. All right, so that answers part A of the question. Get the current in the battery. Actually, it answers part B of the question. Current in the battery, the circuit resistance, the total overall resistance was part A, 20 ohms. We already did that. Now for the tough part, and some thinking is involved, and we have to go backwards here. We want to find the current through every resistor in the original diagram. There was 5 resistors. 5 resistors. Now, so here we go. We got to go backwards with these diagrams. So we go to this diagram here, that's right above the last diagram. Well, it's still a single loop. That means the current flow, and this arrow here represents current flow. Actually, let me do blue on that. Oopsie. Okay, so this arrow represents current flow, so you can see it better. Well, what that means is there's 2.0 amps of current flowing through that resistor and 2.0 amps of current flowing through that resistor, which is important. So actually, I know this is part of the answer over here. This is one of the answers. I want to know how much current is every resistor. Well, that 15 ohm resistor over here, way up at the top, I'm going to go way up at the top, it has 2.0 amps of current. That's one of my answers. Okay. Now, one thing that's helpful at each stage is also to figure out the voltage, the potential difference for each of the individual resistors. And what I'm kind of doing, and I'll circle it in blue right here, I'm going to be using Ohm's law, and I have the numbers simple enough we can do it in our head. But if we go over to, let me change color so it can help us out a little bit here. V equals IR. I'm going to do V equals IR for this 15 ohm resistor. Well, V equals I times R. I is 2, R is 15. So V here is 30 volts. Every resistor has the 3 associated concepts, V, I, and R. The R is given, 15 ohms. The current is 2 amps, so V is you multiply those two. Same thing over here on the right. 2 times 4.8 is 9.6. So that's going to be 9.6 volts. All right, I'm going to round that off to 10 volts. I'm going to round that off to 10 volts to make life a little simpler for us. All right, because V equals IR. I take V is I is 2 times 4.8, 9.6. Because what you'll notice here is that in green, the resistor is, the first resistor is 30 volts, the 15 ohm resistor, and the 4.8 is 10 volts. 30 plus 10 is 40. These have to add up. This is a way to check yourself. It's a lead into what we call Kirchhoff's laws here in a few minutes. Another way to think about this is that the battery is supplying 40 joules of energy per coulomb. It's an energy supplier. The resistors, or the circuit elements, are energy users. They turn energy into heat typically. So the battery is supplying energy at a rate of, or at 60 joules per coulomb. Each resistor is using it up, or this resistor is using it up at 30 joules of energy per coulomb, turning it into heat. This one's, I'm rounding off to 10 to make it a little simpler for us. Okay, now let's bring those concepts back up to the previous diagram. So here's the thing. The 15 ohm resistor is done in a sense. I've got all the values for that. I'll circle it in green. That's all finished. I don't need to recalculate all those, so just keep those in our head or just look at them. Okay, but here's the concept. In parallel, these are each 10 volts, not 30 volts. Where did I get the 10 from? Well, the 10 comes from the previous diagram. The 4.8 ohm resistor is a replacement resistor for 2 resistors in parallel. So this is a very important concept that you have to keep thinking about. In parallel, they have the same voltage. And they have the same voltage as its replacement resistor. That's the important concept. All right, so I rounded off to 10 to make it easy for us. They're each 10 volts. We'll talk more about that with Kirchhoff's laws as well. Well, once you have that, now what you will be doing in that diagram is just using V equals IR. Now let me use blue. We'll use V equals IR to figure out the current in each one of those resistors, because there's going to be more current in the lower resistor. V equals IR. So we have, for the 7 ohm resistor, we have I times 7.7. So the current is 10 divided by 7.7. All right, did I do that? I hope I did. I did that somewhere. It is 1.3 amps. 1.3 amps. It's 1.3 amps. So there's 1.3 amps. I'll come back to that. That's supposed to be an A there. All right. Let me see if I can erase that A. All right, there we go. 1.3 amps. All right, for the 12 volt resistor, or 12.56 ohm resistor, we have, also we do V equals IR. It's 10. I'll do it up here. 10 V equals I times 12.6. Well, let's make that 13. So the current here, 10 divided by 13, is around 0.7. 0.7 amps. Let me explain that. 0.7 amps. It's somewhere between 0.7 and 0.8. Yeah, depending on how you round, you get 0.7 or 0.8. But let me explain this. What's happening here is this. This battery is pushing a current from the battery or all around. There's current everywhere. But that's the 2.0 amps that we started with at the very beginning of the problems, 2.0 amps. What happens is that current comes to this spot right here, the point B. And now it has a choice. It's like 2 coulombs of charge, or you could say it's 200 cars, if I do it proportionally. 200 anything, 200 electrons. Now they have a choice. More electrons, more flow are going to go where it's easier. So basically what happens here is this. 130 go this way, or 1.3 proportionally. And then a different amount go this way, through here and around. That's the 0.7. So I'm using blue arrows to represent the current flow. So what you notice is that 0.7 amps plus 1.3 is 2 amps. In other words, 2 amps of current going into that junction. And then it splits, more going where there's less resistance. But they have to add up to 2 amps. And it's when you round off, because I'm doing some really, a lot of rounding here. If you do this precisely, this was like 0.75 and this is 1.28 or something like that. But if you did it to like 5 decimal places, which we don't need to do, they will always work out, and that's your check. Now, going backwards again. Actually, what I know here is in this initial diagram, I know that there is right here 0.7 amps, 0.7 amps. And I know there's 0.7 amps here, 0.7 amps. And that's the same flow right here. It's the same flow in that branch. They all have 0.7 amps. Because in series, that's the rule. In series, they all have the same current. And that the 8.5 and the 4.11 were the two resistors that gave us the 12.56. That's the branch out there, the outside branch way to the right from B to C has to have that current. All right, so we've actually figured out this now. Let me not circle that. It's messy. But I figured out those two resistors. I have it on a diagram. But now I have to figure out how much current is in these two in the middle here. Now, what happens here is in this little piece right here, there's 1.3 amps going that way. And there's 1.3 amps right here. But that 1.3 amps, I'll make this blue now, this blue dot. Okay, that's 1.3 amps going in. 1.3 amps. But it splits. More current is going to go through the 13.8 ohm resistor than through the 17.2 ohm resistor. But those two, so they're going to have different currents. But what's the same in parallel, once again, is their voltage. They are both 10 volts. All right, they're still 10 volts. They're the same voltage as each other. 10 volts, 10 volts. Because in parallel, they have the same voltage as the replacement resistor, which was the 10 volts for the 7.7 ohm resistor. And then what I just do is I do V equals IR for each of those. I have 10 equals, and you can see how this gets really messy. I'm going to switch to blue again and go way to the left. So for the 13 ohm resistor, I'm going to do V equals IR. It's 10 ohms of resistance equals I times 13.8. So the current in that resistor is, I believe, let's see here. It comes out to be 0.7, well, 0.7 amps. That's the current in this resistor, so 0.7 amps. All right, but then in the 17 ohm resistor, we have V equals IR over here on the right. So we have 10 equals I, that's an I there, times 17.2. So if you do the calculation, you get I equals 0.6 amps. So over here you have 0.6 amps. In other words, I can draw an arrow to represent that. This arrow here represents this, well, these two arrows. The one on the left is 0.7 amps on his base, and the one on the right is 0.6 amps. Sorry. So that says 0.6 on the right hand. So the current splits. 0.7 plus 0.6 though is 1.3. So this is supposed to be a 0.6. So the current, there's 2 amps of current that flows through this wire, gets to point B. 1.3 amps goes down and splits into 0.7 and 0.6. A little bit more going to where there's a little bit less resistance. And then 0.7 going around the outside. All comes back together at point C. And rejoins. 1.3 plus 0.7 gives you 2.0 amps going around back again. So everything adds up. You can see how these, you have to keep organized. You have to remember that in series, 2 resistors or 3 resistors, any resistors in series all have the same current. The ones in parallel have the same voltage. And for the fun of it, and well, also for the purposes of reinforcement of what we just did, I've hooked up this circuit basically that we just studied. I've hooked it up with light bulbs, and I've set all the light bulbs to the same resistance as in or close to the resistance from the worksheet we just did. If I click on this one here, down at the bottom it says 15 ohms. That's what that bulb is. This bulb is 14 ohms, like 13.8 I think it was in the worksheet. They won't let me put 13.8. This one's 17 ohms. this one, I had to do 9 ohms. They wouldn't let me do 8.5. Anyways, they're all set 4 ohms. Okay. Then I set the battery to 40 volts. If I click on that, 40 volts. So what you're seeing here is the brightness of the bulbs, number one. One of the things that makes the bulbs bright is the current. The more the current's the biggest factor for brightness. That's why this bulb right here is the brightest. That bulb is in series with the battery. In other words, the battery is pushing current. I have this battery hooked up opposite of what it showed on the worksheet, just so I could get the current flowing in the same direction. I pointed the arrows on the worksheet. So we say positive flow is going this way. All right, so you can see there's more flow here. In fact, I'm going to measure that flow. So this is in series from this point right here, which is point C, I think, in that worksheet. The current flows this way up and through this branch to this point, point B. That's where it splits. I think in the worksheet, 0.7 amps goes this way around. This is one branch out here. These two bulbs on the right are in series. And that's where the currents join up again at that junction. And these are two bulbs in parallel. Now, in this magic toolkit, not a magic toolkit, over here, there's this thing called an ammeter. It says current, question mark. In real life, they don't look like this. The one that I'm going to show you later on in the future notes, what actual meters look like if you've never seen a multimeter or a meter that measures current or voltage. We'll talk more about that, like I say, in the notes in a little bit here. But this basically tells you the current. Like if I put this on this wire, this crosshair, it says 0.75. Now I rounded off to 0.7 on the worksheet. It actually came out to be like 0.75 if you went to 2 sig figs. So you could have said it's 0.7 or 0.8 to 1 sig fig. I'm going to move this over. But for example, the current in this branch right here, where it goes through this light bulb, 0.57, rounds off to 0.6. That's what we had on the calculation. This, if I put it on that wire, 0.7 amps. If I put on the wire that leads in there before the split, 1.3. Because the 0.6 plus the 0.7 is 1.3. All right? And then, yeah, back up here again, it's the 0.75. It's everywhere the same flow anywhere in this wire, because that's series. So the 0.75 plus the 0.27 gives us then, well, 2 amps going into the battery. That's what the battery's pushing, actually. The battery pushes 2 amps, 2 coulombs per second, up this way through that bulb. So anywhere in that bulb or on that branch, you're going to get 2.02 amps up through this way until it splits again and divides. So that's a summary in visual form of that worksheet that we just did, and it verifies all our final answers. Like I say, in the future we'll show you how to measure voltages with this meter right here that I'll just pull out. That's a voltage meter, or they call it a voltmeter. So stay tuned for that. But there we go. To say it one more time, in parallel, 2 or more elements, resistors, have the same voltage. In series, they have the same current. And like I say, we'll measure voltage in a little bit here.